Today we will continue our discussion of the area under the curve, and we will define a new object called the definite integral, which will give us that area. Now recall from the last discussion, we were approximating areas under curves using rectangles, cutting up the base into equal pieces using the height of the function to determine one dimension of the rectangle. So function value height, delta x, the width, and delta x was the length of the interval, b minus a, divided by n. You add up all of these, and you get an approximation for the area. What we decided was, when you cut this thing up into n pieces, did that, and let n go to infinity, you got the area. This is what we're going to call the definite integral. This symbol, integral from a to b of f of x dx, is equal to this sum, which you will recall is a Riemann sum. And this is called the definite integral of f of x from a to b. It gives the area under the curve y equals f of x between x equals a and x equals b. Now, there are some consequences to this definition. Let's look at the following picture, and here we're using left-hand endpoint rectangles. And when we come to this particular rectangle, we note the base is delta x. The height now is given by the function value, which is negative. That means that the product of the function value and delta x is negative. That's going to count as negative area. So area below the x-axis is going to count as negative with this definition. Next thing, suppose instead of going from a to b, we go from b to a, reverse the so-called limits of integration. What happens is delta x is not b minus a anymore, it's a minus b over n, 0 minus 2 over 8 minus 0.25 as opposed to 0.25. Now delta x is negative. That makes everything negative. So the definite integral from b to a is the negative of the definite integral from a to b. Here's a picture that suggests another property here. Here's our function y equals f of x. We go between a and b, and this area is given by this definite integral from a to b. The area between b and c is given by this definite integral between b and c. The whole mess should be the definite integral between a and c, and what you get out of this is the definite integral from a to c of f of x dx is the integral from a to b plus the integral from b to c. Another thing that we can see here from the definition is if we look at our function and this first rectangle here, the height is f of a, the width is delta x. Now let's multiply our function by a constant. That doesn't do anything to delta x, but it scales this height up by a factor of c, which means that this area is scaled up by a factor of c. That's true about all of the rectangles. Consequently, the integral from a to b of c f of x is just c times the integral from a to b of f of x dx. What happens when we add two functions and integrate? Well, if this is the function f of x plus g of x, we can see this height is going to be f of a plus g of a. And we get a little red rectangle here, which is exactly the sort of rectangle we would get if we were doing a definite integral of f of x. We get a green rectangle, which is exactly the rectangle we would get if we were doing a definite integral for g of x. And you add those two areas, and you're getting this one, which means that when we integrate f of x plus g of x between a and b, it's the same as integrating f of x between a and b plus integrating g of x between a and b. And that's another property of the definite integral. Suppose our function is a constant. Well, in our region, it's actually a rectangle. The length of the base is b minus a, and the height is c, the function value. And obviously that area better be the area of that rectangle, which is c times b minus a, and that is in fact exactly what's true. The definite integral between a and b of c dx is c times b minus a. Now let's look at some examples and put into use what we've just talked about here. So here's our function, and let's first look at the definite integral from 1 to 2 of f of x dx. Now if we look at this, we can see 1 to 2, height, we've got this little rectangle here, length of the base is 1, height is 2, area should be 2, and that is in fact exactly what the definite integral is. Now let's look at the definite integral between 2 and 5, and that's from here to here. Now notice there's some stuff above the axis and some stuff below the axis. The stuff above the axis counts as positive area, and this is height 2, that's length 1. 1 times 2 is 2, and since it's half base times height, this has area 1. Length here is 2, height is 4, 4 times 2 is 8. 1/2 of that is 4, but now it's negative, so this is a plus 1 and a minus 4. And the answer is minus 3. Now let's look at the definite integral from 2 to 0 of f of x dx. And when we look here, 2 to 0 is here, our height is this. Notice, however, that it's colored pink and not green, and the reason is we're going from 2 to 0, which means our delta x's are negative. Negative times positive is negative. This counts as negative area. 2 times 2, negative 4. Now, let's look at the definite integral from 1 to 5 of f of x dx. Now, if we look at this, we go from 1 to 5. That's the same as going from 1 to 2, plus from 2 to 5, and we've done both of those. From 1 to 2, the definite integral gave us 2. From 2 to 5, the definite integral gave us minus 3. So if we go from 1 to 5, we get the sum of those, 2 minus 3, or minus 1. Again, this integral plus this integral gets us the integral from 1 to 5. Finally, let's talk about the integral from 5 to 5 of f of x dx. And that's the area under the curve between 5 and 5. There is no area. The area is 0. The integral is 0. Thinking about definite integrals as areas under curves allows us to evaluate some fairly complicated looking expressions. So let's consider here the definite integral between 0 and 4 of the square root of 16 minus x squared. Now the idea here is to think about this is it's the area under the curve y equals the square root of 16 minus x squared between 0 and 4. Now if we look at this curve and square both sides, we can see that y squared is 16 minus x squared, and that gives us x squared plus y squared equals 16, which we recognize as a circle of radius 4, as 4 squared is 16. The area of such a circle is going to be pi r squared, so you might think that the answer is actually pi times 4 squared, or 16 pi, but we need to look a little more carefully. Here's our circle, as described by x squared plus y squared equals 16. But one of the things that we notice is the original function y equals the square root of 16 minus x squared is always bigger than or equal to 0, which means that this section of the circle is not included in our area calculation. The next thing to notice is that this area goes from -4 to 4 for x. However, the limits on our definite integral are 0 to 4. So the section between -4 and 0 is not included. And finally, we only have this little green section as the area represented by this definite integral. And that's 1/4 of the circle. So we end up getting 1/4 pi r squared, where r is 4 here, and that's 1/4 16 pi, or 4 pi, which is this area. Let's look at an even more complicated definite integral, the integral from 0 to 2 of the square root of x cubed plus 6x plus 16. Now, this definite integral is sufficiently complicated that we can't actually find the exact area, but we can estimate where that area lies in terms of magnitude. And what we do is we look at the graph, and you can see that the graph is that of an increasing function. The smallest value on our interval between 0 and 2 happens at the 0 endpoint, and if you plug in 0, you get the square root of 16, or 4. The largest value occurs at +2. If you plug that in, you've got 8 plus 12 plus 16, which is 36. Square root of 36 is 6. So this is the picture that we're looking at. We want this area. We know that the low point on the function over the interval is height 4. The high point is height 6. So what we can do is the following. We can draw a little rectangle from the low point, and we see this rectangle has height 4. Length of base is 2, area is 8. We're guaranteed that this area is less than the area described up here. We draw a big rectangle using the high point. We can see that this height is 6. The length of the base is 2. That area is 12. And one thing we can say for sure is the integral we care about is bigger than or equal to 8 and less than or equal to 12. And this is a general principle here. If you've got a function and you know where the low point is and you know where the high point is, the definite integral under the function between those 2 points is going to be low point times length of interval, and it's going to be less than or equal to high point times length of interval. And that works out to the following. If on AB, the lowest value f of x takes on is small m, the biggest value that f of x takes on is big M, then smallest value times length of interval is going to be less than or equal to the definite integral, is going to be less than or equal to largest value times length of interval.